All right, welcome to Limits Numerically. This is where we're going to take an approach on limits with numerical tabular data and see what we can do to evaluate limits with numerical data. All right, what is a limit? Informally, L is the limit of f of x as x approaches c if we can make f of x as close as we like to L by requiring that x be sufficiently close to, but unequal to, c. The notation is L equals the limit as x approaches c of f of x, and it is read in that way: L equals the limit as x approaches c of the function f of x. So here's a graph of our value as we approach the value c, and as we get as close as we like, okay, to L by requiring that x gets sufficiently close but unequal to c. So we're trying to kind of sandwich it in between the value c to get as close as we like to the value L. Example 1. Here's a table of data, and what we're going to do is we are going to look at how we could write this in terms of a limit, and what do you suppose is the value of the limit. So we're not being given an algebraic equation, we are just looking at tabular data. All right, so what limit is being considered? Well, in order to look at this, we have to look at what x is approaching and trying to get sufficiently close to. And if we take a look at this, it looks like x is approaching the value 5 from the left and right-hand side. So the limit is as x approaches 5, and we're given the function f of x. What do you suppose is the value of the limit? So that is the L value, or the output that it's approaching if we can make x very, very, very close to 5. And that value looks like right here, as we're getting closer and closer to 5, those two values right there, it looks like from the left and right-hand side, the limit value is probably 22. So the table of value, oh, this is our example, sorry, finished out. It says the table suggests that f of x is getting getting as close as we want to 22, as long as we keep x sufficiently close to 5. So here's our 5 value right here we're trying to approach, and we're going to keep it getting very, very, very close to the value 22. For example 2, we're going to suppose we wish to approximate the limit as x approaches 2 of the rational function x to the third minus 2x squared divided by the quantity 3x minus 6. So how can we do this with tabular data? We can make a table. If you go to your calculator and go to second window, which is our table set, we can change the independent variable to ask. Okay, please leave the dependent variable as auto. And we're trying to find the limit as x approaches 2. Okay, so if we plug in the number 2 directly into the problem, we're going to get 2 to the third minus 2 squared divided by 3 times 2 minus 6. And what's going to happen is we're going to get 8 minus 2 times 2 squared is going to be also 8. And then on the denominator 6 minus 6, we're going to have an approach, I'm going to put an arrow here, 0 over 0, which is actually indeterminate. So what we're going to do is we can't plug in the number 2. So what we have to do is we have to pick out numbers very, very close to the number 2 from the left and right-hand side. So a table is a very good feature for that. So in that table, we need to pick numbers that get closer to the number 2 from the left and right-hand side. So how can we do this with our graphing calculator? Please make sure that you place our function under y sub 1. Okay, and then again, you're going to go to table set under second window. You're going to change it to ask. We've already done that prior to this, or we should have. And then what we're going to do is we are going to put in data points that get close and close to the number 2. So here are the data points that I'm getting. I typed those in under second graph, is how you go to your table and you can put in values that are closer to the number 2. So for example, 2.5 was 2.0833, 2.1 was 1.47, and we're getting closer and closer to the number 2. So at 2.001, we have 1.335, 1.347. Okay, and then I'm coming from the other direction at 1.5, and if you come down here, 1.999 is 1.322. So between these two, we are looking at what does it seem to be that the number is approaching. So the limit as x approaches 2 of the function 3x, or x to the third minus 2x squared minus divided by 3x minus 6 is approaching a decimal value. It's not a very nice value. We're approximating that, so I'm going to get rid of this, put my answer. And it looks like it's approaching 1.3 repeating, possibly. You could round it and say 1. You could take the average of 1.3347 and 1.322, but about that number. So we are approximating our limit by using a table. Okay, we cannot strictly evaluate the limit at the number 2. We get an indeterminate form of 0 over 0, and we cannot evaluate the function at that point. So the function doesn't exist at 2, but the limit does. And that is a big distinction that we're going to be emphasizing as we go through this chapter, that a limit can exist and a function doesn't have to, or vice versa. So in this case, we cannot evaluate the function at x equals 2. We get an indeterminate form of 0 over 0, but we can find the limit as x approaches 2, and we get about 1.3 repeating. All right, example 3, I encourage you to pause the video and try this on your own. Okay, so what limit is being considered? It looks like the limit as x, and we're seeing what is x approaching. So from our table, this is just horizontally distributed, just to kind of give you a different view. It looks like it's approaching the number 0 from the left-hand right side. And what is our function's name? It is g of x. We do not have the equation, so it's going to be g of x. And then over here, suppose what is the value of the limit? So what is the output? So the limit, I'm just going to rewrite that real quick, as x approaches 0. So we have our limit, our x approaches 0. It has to have 3 parts to it of the function, happens to be g of x. And it looks like the outputs are approaching the number 1. So that is a horizontal arrangement and reading it from tabular data with no equation. All right, example number 4. Same 2 questions. What limit is being considered and what do you suppose the value of the limit is? Again, please, I encourage you to pause the video and try it on your own. All right, so this one has a little bit different data. We are looking at numbers for t from the right and left, it looks like, of the number 3. So this is the limit as x, there we go, careful, as t approaches 3. And we have our function without the equation, though, h of t. So it's important that you use the right variables here. The limit is t as t approaches 3 of the function h of t. And what do we suppose that limit is? So I'm going to, again, just rewrite it for good habit's sakes, of h of t, and it is approaching the output. Be careful here. The limit is approaching from the left and right-hand side the number, what looks like 7. It does not matter that the function seems to have an output value of -4. So it's as x approaches c, but unequal to c is the definition of the limit here. So we aren't looking at what the output is at 3. We are saying as x gets sufficiently close to the number 3, what is the L value approaching? And it's approaching the number 7. All right, example 5. What is the limit being considered? And what do you suppose the limit value is? Again, feel free to pause and try to answer those 2 questions on your own. Here, it's the limit as theta approaches. So we have our input theta and our output r of theta. And it looks like from the left and right-hand side, we are approaching the number -2 of r of theta. Okay, and that output, this one's kind of demonstrating that it does not have to be neat numbers. All right, it does not have to be a fraction or an integer that it's approaching. It can be pretty ugly. So this one, the limit as theta approaches -2 of r of theta, seems to be approaching this number right here, -2.72629. So we'll round it to -2.73. And again, that's not necessarily 3 decimal places. We could average those 2. We could say split the difference between 6 and 9, 7, something like that. Okay, but it is an approximate. I'm going to change it to approximate symbols with that. So it expands our idea of what variables can be used, theta, it can be messy numbers, and such forth. All right, example 6, consider what limit is being considered and what do you suppose the value of the limit is. Again, try this one on your own. All right, so this one's also trying to demonstrate that you don't always have to be approaching an integer. Okay, it looks like from the left side we are approaching 3.399, and then from the right side we're getting numbers closer and closer, and we get 3.401. So it says the limit in our function, we don't have a function name for this, but we have a variable k. So it looks like we're approaching the number 3.4, and we don't have a function name. So we are going to rewrite the function right here, k squared minus 25 divided by k minus 5. You could assign a variable name of f of k, I guess, to this, but you can just rewrite it as well. So the limit as k approaches 3.4 of this fraction, k squared minus 25 over k minus 5, is giving you a value of about, looks like 8.4. So that is how we can read tables with a variation of nice integers, non-nice integers, and it's not always going to be pretty perfect integer values. All right, example 7 looks very similar, but this time we are approaching a little bit different. Okay, so again, what limit are we considering, and what do we suppose the value of the limit to be? So the limit, what we're considering is what are we approaching, and we are approaching from the left and right hand side the limit as k approaches the value 5. So we're trying to approach as close as we can to 5, but unequal to 5. So get sufficiently close to that. And our L value, our output, so we have our k squared minus 25 divided by k minus 5. It looks like right here is what we're looking at. It is approaching the value 10. I guess that goes down here, so it's approaching the value 10. And again, I just want to point out the limit exists even though we cannot evaluate 5 in the function. So 5 squared minus 25 divided by 5 minus 5 gives us a value or approaches the value or indeterminate form of 0 over 0. So even though 5 does not exist in the domain here is all real numbers except for 5, because we're dividing by 0 then, we can't evaluate this function at 5, but we can find the limit, and the limit is approaching 10. And again, that's a big distinction between evaluating a function and evaluating a limit. All right, one more here, example 8. Consider limit and what do you suppose the value is? I again encourage you to pause the video and try that on your own. All right, so what limit's being considered? It looks like we're approaching from the left and right of 0, and we have an n and a q of n. So this is the limit as n approaches 0 of q of n. And what limit or value are we approaching? For q of n, we are trying to get an output value. It looks like this one's interesting. So from the left, we have 1.999, and from the right, we have negative 3.001. So this limit does not exist. And so we're going to go into a lot of detail on that right now. But one of the main things is that if the left side and the right side are not approaching the same value, then we will not have a limit that exists because they're not approaching a single value for L. One side of this is approaching 1.999, while the other side's approaching negative 3 roughly. So limit does not exist because outputs do not converge on a single number L. Might come back to this example when we're later, and we'll talk about one-sided limits. We will talk about how to evaluate those as well. But for now, this limit does not exist because the left side and the right side are approaching different values of L. Okay, for example 9, again, I encourage you to pause the video and say what limit is being considered and what do you suppose the value of the limit is going to be. Okay, so for this one, we are given J, and it looks like from our table, from the left and right hand side, we are approaching, it looks like 0 from the left and right hand side. So this is the limit as J approaches 0 of the function. We don't have a name, but it's 5 over J. We have the equation. Sometimes that's even better. And notice that the table is left blank as for the output. So you would go to your graphing calculator, put this in y sub 1, or evaluate it simply on your main screen. You can use the table feature that we demonstrated earlier. And I would take 5 divided by 0.1 and so forth, and I should get values. See, we're going to get 50, and then we'll get 500, and we're going to get 5,000, 50,000, and you'll start seeing a pattern. Then when I plug in negative 0.0001, I get negative 50,000, and then I get negative 5,000, negative 500, and negative 50. So what do we suppose the value of the limit is? Again, it is approaching two different values from the left and right hand side. Actually, with 5 divided by j, x can never equal 0, so we're evaluating a limit where the function can't be evaluated. So again, that's important to note. But what is happening graphically, or with a property of this function, of this rational function, is we approach 0 of this, of 5 divided by j, it's actually approaching a vertical asymptote, and from the positive side, we are shooting off to positive infinity. I know it's 50,000 here, but if we kept going and going, shrinking down towards 0, we'd shoot off to positive infinity, and then at negative, from the left side of 0, we are shooting down towards negative infinity with this negative 50,000. So this one is a does not exist. And I'm going to show you a little bit of notation here. So the limit as, not x, j, approaches 0, and we're going to put a little bit of a negative symbol. It's not a typo, it means from the left, of 5 divided by j, and that is approaching negative infinity. And the limit as j is approaching 0, and we're going to put a little plus sign for from the right of 5 divided by j, is approaching the number positive infinity. So since these are not equal, and you can never actually equal infinity or negative infinity as well, but since they're not equal, then the limit does not exist. The number one reason that we will typically see for limits failing to exist is that they are not approaching the same L value from the left and right hand side. So we will go into much more detail with that, but this is kind of our first example with some little bit of notation with that little superscript of the minus symbol and the plus symbol. They're not approaching the same value, therefore the limit does not exist. One-sided limits is what if we wish to consider a limit of the function f of x as x approaches 3 from the left. So with that last example, with number 9, this is how it's going to kind of look with notation. Okay, it's going to be the limit as x approaches 3 of the function f of x, and we want to do it from the left. So we're going to put a little left symbol right there. So again, there's no function here to kind of evaluate, just showing you some notation with that. Limits can fail to exist for 3 reasons. Okay, and these reasons are going to become more important as we go through the more chapters, but there are going to be 3 big reasons. And the first one that we've already explored today is 1, the left and right sided limits are unequal. Okay, that's a big one that happens most of the time. The second reason a limit can fail to exist is the limit becomes infinite. Okay, that means it grows without bound to positive infinity or negative infinity. And since we defined limits with as it approaches a value L, it has to be a number, a real number, and infinity is not a real number. So a limit can fail to exist if the limit becomes infinite as the x approaches that value. And then the third one, it will come up again, we'll bring that up when it's appropriate, but we'll put it down there now, is due to what's called oscillation. Okay, and oscillation means kind of like an oscillating fan. It goes up and down, but it's not approaching or settling in on a number. It's shooting off and getting bigger, or it's just not approaching a number at all. So we'll go into much more detail about oscillating But if it doesn't settle in towards a value of L from the left and right hand side, the limit will fail to exist. So those are just a preview of some of the examples and reasons why limits will fail. So again, a couple notes for today. A function value does not have to exist in order for the limit to exist. So we may not be able to plug in the value 2 into the function, but we could still get a limit value. The limit value is independent of the function value. So the function could have an output of 7, but the limit could be approaching the number 2. A limit may fail to exist altogether, and we just talked about that. The number one reason why is if the left-handed and right-handed limits or sided limits are unequal and not approaching the same value, if it grows without bound to infinite values, or due to oscillation. Okay, thank you.